This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
Welcome to SE Radio. My name is Johannes and I'm here with Ken Collier, and I will read you the biography of him. Ken is author of Agile Analytics, a value-driven approach to business intelligence and data warehousing. He is a pioneer in combining agile methods with data warehousing, business intelligence, analytics. Ken has written extensively about Agile Analytics for the Qatar Consortium and his blog, theagilist.com. So, welcome to the show, Ken.
Thank you. Happy to be here.
Is there anything you want to add to your biography?
No, except that I am the director of advanced analytics for ThoughtWorks, and we have data science teams all over the world working on analytics.
So, can you start with explaining maybe what analytics means in 1 minute or so?
Sure. So analytics is a very large umbrella term. It ranges from descriptive analytics. Most companies have business intelligence reporting, dashboards. It's sort of like looking in the rearview mirror, finding out what has happened. Then we move into predictive analytics using techniques like data mining, statistical analysis, machine learning for anticipating or probabilistically predicting what might happen or what is likely to happen. And then at the far end of the spectrum is prescriptive analytics, where we can actually use analytics as a way to influence shopping behaviors or operational behaviors or things to happen. So analytics kind of runs the spectrum from business intelligence to what we now call data science, which includes machine learning, data mining, and statistics.
So what would a typical analytics project look like? Can you give a plastic example?
Sure. Actually, there's a couple of different examples. The most interesting projects are projects where analytics is part of a bigger solution. So, for example, I'll use something that Amazon.com is working on. In North America, and I suspect this is going to be true in the rest of the world, it costs a lot of money for Amazon to ship items across the country. America is a very large country, and it costs a lot to ship from one coast to the other. So they're using data science and predictive analytics to anticipate what you might order, based on your browsing, based on your past orders, past shopping, similar to the way that Amazon recommends items that might interest you. Now what they're moving into is the ability to predict ahead of time when you're going to order something, and they use that to ship the item closer to you, not to your doorstep, but they ship it to a hub near you so that when you do order it, they can get it to you very quickly without a lot of extra cost. So that's called anticipatory shipping. And so the project itself would include a lot of data science to figure out how to make those predictions and when to take action on those predictions. And then the bigger solution is the problem of moving items and deciding when to move the items near you.
So can you elaborate a little bit on how they actually find out that you might be interested in it?
Sure. So there are several techniques that are used for these kinds of things. For recommendation systems, we often use a technique called collaborative filtering. One use of that technique is to look at the characteristics of the shopper. So let's think about Johannes characteristics, your age, things that you've bought in the past, what you like to do, lots of information about you, and we can look for other people that have similar characteristics, and we can say, these other people have purchased these items, therefore you might like this item as well. That's called collaborative filtering from a shopper to a shopper. Item by item means if you're browsing a book on Amazon, or you're browsing an item in the store, we can look and see so people who bought that item also bought other items. What kinds of items did they buy that are in common? And that can lead to recommendations as well. So that was a recommendations scenario. For that anticipatory shipping, what we do is we look at the data, at the past data of your behavior, when you ordered things. Maybe it's something like you browsed one day, and on average 4 days later you ordered the item. So maybe there's a pattern that can be uncovered through multiple searches on the website. I don't work for Amazon, so I don't know exactly what they're doing, but that's the sort of thing that we would do to do that kind of prediction. So each problem we apply a different algorithm, but what's fundamentally different with analytics from programming other solutions is that instead of using a rules-based system, a series of if-then kinds of rules to make a decision, we use a fuzzy matching or a probabilistic reasoning based on a load of past data. We're detecting patterns in the data that support a high likelihood or a high probability of something like that occurring again. Another example of this is credit fraud detection. So when shoppers use their credit card, the credit card company knows what your normal behavior is, and if your if the transaction looks unusual compared to what you normally do, it might get flagged as a likely somebody stole your credit card. So that's another use of predictive analytics. And it's all based on large volumes of data.
Yeah. You mentioned data science a couple of times. I've heard the term data scientist as well. So what is data science, and what does a data scientist do in his daily life?
Yeah, this is a good question. So the term data science is a relatively new term, or at least it's become popular only in the last 2 or 3 years. The phrase, the term was coined to describe somebody who goes beyond statistics and probability. Often we find data scientists in the hard sciences. So at ThoughtWorks, our team of data science in North America are PhDs in physics and chemistry and the sciences, where what they have learned are a set of skills for collecting massive amounts of data. So for example, one of the data scientists that I work with is he's an astrophysicist, so he's familiar with collecting large volumes of data about space, stars and galaxy information, and analyzing that to possibly look for detecting black holes or look for new planets, that sort of thing. So data scientists, they have strong statistical analysis skills, but they also know how to program. They know how to manipulate data into a format that's mineable or discoverable. They have a spectrum of skills that go beyond just statistics. They also know about machine learning, which actually comes from the computing sciences. So they kind of blend together mathematics, computing science, computational sciences, the ability to rigorously apply scientific methods, so hypothesis testing and experimentation. All of these things come together to create this role called data science. And what we're seeing, I don't know how much this is true in Europe, but what we're seeing in North America, Are more and more universities are starting to offer degree programs in data science or analytics, and they tend to be multidisciplinary. So it's not just in computer science, it's not just in research sciences or mathematics, it's a blend of all of these things. And so that's, so data scientist, it kind of describes a very special mix of skills.
But when I look at it, those people are more there for like the conceptual side of formulating hypothesis and then like feeding it into the systems. Are those people also programmers, or do they have people who realize this for them?
No, so a good data scientist will they'll do their own programming, and most data scientists today are using languages like R or Python. MATLAB is a popular programming environment. SAS, SAS those last two are commercial tools, whereas R and Python are free languages. Having said that, data scientists aren't typically, I wouldn't call them software devs with all the discipline and practices that good software developers use. So to some extent, they're hackers. We often, at ThoughtWorks, we often try to pair a data scientist with a dev so that the quality of the code that they write goes up. So it's not, so the data science, the role of the data scientist is to take a business question, or it could be a business question, it could be a question from some other domain, but it's some practical question, like, as an example, if I'm running a grocery store and I offer a coupon for 20% off of peanut butter, I might lose money on that, but can I predict when people will continue to buy peanut butter because I gave them that very first coupon? So that's the business question. Should I invest in giving these coupons for items, and what can I expect? What kind of behavior can I expect after that? So that's the business question, and the data scientist has the ability to say, I can turn that into an experiment, and I can use all of this data to analyze who is likely to use that coupon and then continue buying peanut butter at full price after the fact. So I don't know if that example made sense, but that's the data scientist sort of takes the business question and turns it into the research question, and then they write the code to do that. Now, in the example, the Amazon, the example I used earlier of what they call anticipatory shipping, the data scientists, the business leaders who have the idea of saving money by shipping items before they've been ordered, that's the big idea. And then the data scientists, their role is to say, all right, well, how can I collect all the data that I need to make good, relatively accurate predictions to go ahead and do that shipping. And so the data science work is a component of that bigger solution.
So he is not only responsible for like analyzing the data when they're there, he's also responsible for like having ideas or finding out which kind of data I should actually gather to make a prediction.
Yes. Yeah, that's exactly right. And so a good data scientist needs to not only have those good analytical skills, they need to have some domain knowledge. They need to understand the data that how to interpret the data, how to manipulate the data. So there's a lot. In fact, we often say that about 80% of data science is really spent just wrangling data, just getting the data into a format that's ready to be analyzed and mined and modeled. And so there's really a lot of work, preparatory work, before you start making the predictions. So it's
this is something like you would do with a data warehouse, capturing the data and bringing them into a form to analyze them.
Yeah, very possibly. So data warehousing is interesting. The purpose behind data warehousing is to pull information out of your operational and transactional systems into a format for analysis. Now, most data warehouses, most conventional data warehouses that have been built over the last 20 years have generally been for the purpose of doing business intelligence reporting and executive dashboards or dashboard presentation of data. So often the data is structured in a way that lets people drill down to low levels of detail or aggregate up. So it's sort of examining and exploring the data. But a data warehouse could also serve up data that is prepped in a different structure for this kind of data science work that we've been talking about. It's kind of interesting that umbrella term analytics that we talked about earlier. There's a lot happening in there. Data science and business intelligence are two very different sets of skills. So BI developers that build in tools like MicroStrategy or business objects are not the same people that are doing data science work and building these predictive models.
Maybe you can elaborate a little bit on what business intelligence actually means.
Sure. Yeah, so business intelligence is a field that's been around for 25 years or so. The goal of business intelligence is to give data-driven decision support to executives and business leaders who need to make decisions. So it could be financial data for making, for analyzing and forecasting the next year of business or the next quarter. It might be human resources data to make sure that you've hired the right people and they're performing well. It could be transactional data to see when you need to. If I'll stick with retail as an example. Many retailers use business intelligence as a way to know when peak sales happen so they can staff the stores or stock the stores appropriately. So business intelligence is generally that descriptive or rearview mirror facing analysis that I talked about earlier. Data science, on the other hand, is more in the predictive and prescriptive end of that range, and it's the skill set that we've been talking about with people programming in R or Python, doing experimentation and research. So very different skills, very different tools and techniques, still fits within that, spectrum.
So business intelligence is rather about presenting the data in an easier consumable form, and analytics is like deducing stuff from them.
That's exactly right. That's a good way to say that. And there's a term, an acronym that we use a lot in business intelligence called OLAP, online analytical processing. And what a lot of data warehouses do is they structure the data for online analytical processing. And what that means is that the data can be sliced, it can be, you can take subsets of the data easily, you can filter the data easily, you can drill down to low levels of detail like individual transactions and customers, or you can roll up the data to store level or city level groupings of aggregates of the data. So that's business intelligence revolves a lot around that sort of ability to drill and slice and dice the data.
So with data warehousing comes this notion of a extract, transform, load mechanism, ETL. You see it everywhere.
Yep.
What is it, and how much does it play into the work of a data scientist?
Okay, that's interesting. So ETL is in the data warehouse world, is the bulk of the programming. It's usually done using a tool, tools like Informatica, Ab Initio. There's some open source or semi-open source tools like Kettle, which is part of Pentaho. I won't rattle off all the names, but these are tools that enable the ETL developers to extract data out of the source databases, so the transactional systems or operational systems, transform the data into the structures that it needs to be in, and load that data into the warehouse. So you can think of those steps as being the processing steps needed in order to populate the data warehouse. The challenge with ETL, if you look at large, expensive data warehousing projects, the largest component, or at least one of the most expensive components of data warehousing projects, is ETL. Creating the ETL, testing it, making sure it's working properly, and then ongoing maintenance and support of ETL is quite expensive. One of the things that I've been talking a lot about lately is ingesting data differently. So the traditional way of ingesting data into a warehouse is doing that extraction into an integration layer in a multi-layered architecture, doing your transformation and business logic to enhance and restructure the data, and then loading it into the warehouse. And so therefore there's a lot of complexity that lives at that integration layer in a three-tiered data warehouse architecture. So something I've been talking about is extracting data into a data core. Some people are referring to this as a data lake, which is often using a NoSQL technology like Hadoop or something like that. Simply grabbing the data, moving it into that core or that lake, and then only dipping data out as you need it, when you need it, for the applications that need to be supported. So for example, if you're going to populate an executive dashboard, you say, well, what data does that dashboard need? It's a subset of all of the data. So we'll just go grab just that data. We'll structure just that data to support the dashboard. And then the workload is smaller because you still have to do the transformation, but now you're doing transformation on just that subset of data so that the dashboard
so that you just have the data you need.
That's right. So the design principle is just in time, only take what you need when you need it, and only transform what you need when you need to transform it. Oh, you had one other part of your question that I didn't answer. You asked how it's relevant to data scientists. Data scientists ingest data into their... Actually, it's interesting. We talked about that slicing and dicing in business intelligence. Data science actually does something almost opposite of that. So typically in data science, what we do is we combine the data into one flat, wide table. If you think of it as structured column data. So we want big, wide data with lots of features or attributes in the table, whereas a relational database has lots of tables that are connected to each other. Data science denormalizes that data. So ETL doesn't play a big role in data science. ETL plays a much bigger role in data warehousing. Most data scientists prefer to go straight to the source or grab the raw untransformed data into their data science feed. So there's some different, this creates an interesting challenge because data warehouses are often designed to support business intelligence, and they have to be rethought in order to support the data scientists because it's a different kind of thing.
Yeah, I was thinking a little bit is along the lines, isn't like the transform of this ETL the job of a data scientist when you look at it from
there is some transformation that data scientists do. So the transform, let me think of a good example here. So for business intelligence, I was on a project some time ago where we needed to calculate gross profit, net profit, and cost of sale. Those were three calculations or transformations that we needed to do in the warehouse. There were others as well. Those particular calculations were quite complicated, this company. This was a company that sells streaming video, and they have to pay the studio a royalty fee. There's a lot of fees that move around when you enable people to watch a movie online or on their TV. So the calculations were quite complicated. Those transformations needed to happen in order for the business intelligence tools to do their job. Now, we also did some data science work on that project. We did some predictive modeling. And as it turned out, we didn't take advantage of those are called calculated measures. We didn't take so much advantage, or the data scientists weren't so much involved in that transformation logic. They simply used that data as additional features in the predictive analysis. Now, what data scientists will often do is what's called feature engineering. So, in the world of statistics and machine learning, we talk about what we call a target variable, which is in my credit fraud example, the target variable is whether a transaction is fraudulent or not. Whether, what's the probability that it's fraudulent or not. So you could say yes or no, or you could say a percentage, but it's one field in the data that is the prediction. Now, all of the other fields that are used to make that prediction are called features. So the more features we have to work with, the more likely we are to come up with patterns that will make a highly accurate or a higher degree of accuracy. So feature engineering is sort of like transformation. It's where we're using singular raw features and combining them to create yet another feature and maybe another and another. So kind of like the calculation of net profit, where we used raw data in a formula to create net profit. A data scientist might do something similar, but it's for a different purpose. The data scientist doesn't create the business logic. They just simply use the results of that. Does that make sense?
Yeah, I'm wondering a little bit about, if you talk about multiple features, don't you run into the problems of multiple testing problems where the predictive value goes down because you use too many information?
Oh, so yeah, this is an interesting, this is a skill that data scientists have. So not all the features are meaningful. In fact, there's a lot of noise and a little bit of signal. And so we're looking for the signal in the midst of all that noise. And what we want is to find the features that have the highest correlation to make the prediction, and we want to get rid of the features that don't seem to influence the prediction. So starting with more features is good because there's a likelihood of getting better predictability, but it means that you're carrying all those features that aren't useful, you're carrying them along. So what we do is we start pruning. We want to do feature engineering to make good features, and we want to do pruning to get rid of features that aren't helpful. So there's this it's sort of part of the process of trimming down your data set to be the features that are the most meaningful and matter the most.
Going back a little bit to data warehousing, I've heard that you promote something called the agile processing pipeline. Some clients apparently call it Kenfrastructure. Can you elaborate a little bit on about what this actually is and why you think people should consider it?
So this is actually what I was describing earlier when I was talking about the data lake or the core. That's part of this agile data processing pipeline. So my argument is that conventional data warehousing it's too expensive and it's prone to failure. In my book, I talk about how you can use agile development technique while still using a data warehouse architecture that we've been using for quite some time. Those architectures aren't bad, but the conventional data warehouse architecture tends to say, let's extract all of the data, let's do a full source discovery, extract all the data into the integration layer, apply all of the transformation logic, and then load that data into the warehouse. And most conventional data warehousing projects try to boil the ocean. I don't know if this is a term that's familiar in Germany, but
not really.
The metaphor means trying to do everything all at one time, trying to grab all of the data, trying to figure out all of the transformation logic
Big
and load
design
all
up
of
front.
that data. Yeah, big design up front. It's very similar to that. So that's a fundamental problem, and so my book says, go ahead and use conventional architectures, but do it in an agile, iterative fashion, pulling data a little bit at a time all the way through your architecture. The agile data processing pipeline that one client has started referring to as the Kenfrastructure it takes this a step further. It says, now that we're pulling just what we need when we need it, let's move the transformation logic as close to the business as possible so that you can pull data quickly, cheaply, scalably into the lake or the core, and then you can dip out of that core only what you need, and then apply the logic at that outer or the final stage in the architecture. So I think of it, I actually have pictures of this that I draw kind of as concentric circles, where the innermost circle is the core. You want to ingest data into that core cheaply and easily, so that you can just put data in there and not have to think about how it's going to be used. And then there's an information layer around the core, where the information layer is the it's a publish and subscribe model that says we will dip the data out of the core, structure it in the right format for its intended purpose, and then the application sits on top of that information layer. And the information layer, you might have 4 or 5 different ways to structure the data. So you might use a relational database for one purpose. You might use a graph database for another purpose. You might use a column family or another NoSQL technology and so each of those data stores is purpose built, and you can drive the logic there instead of having a bunch of transformation logic living in the middle. So combine agile development practices with this agile processing pipeline, and you've got that gives the team a lot more ability to move quickly and adapt easily.
When you will send me this thing, I can put it in the show notes.
Oh, okay, yeah, I'll do that.
You said something about it's a publish subscribe mechanism. That means like the transactional data store is giving me information when it stores data into it, and I can react to it? Or?
Yes. Oh, so that's actually, I'm glad you asked that, because another characteristic of this agile data processing pipeline is that instead of doing so conventional data warehouses pull data, the code reaches into the source databases and pulls the data in, usually on a nightly batch basis. What this processing pipeline does is it drip feeds the core by instrumenting those source systems to send messages, to put messages on a message bus, or you can use other techniques. There's a technology that is often used with Hadoop called Kafka, and it's a sort of messaging type system, or you can use a pub/sub technique as well. But the idea being that instead of doing nightly batch movement of data, you're just, as data arrives in the transactional system, it just immediately gets published onto the message queue, and where it can get consumed by the data core and by any other systems that need it.
In contrast to the data warehousing, from a traditional sense, you have a more immediate feedback on your data viewing application.
You have the ability to do what's fairly close to real-time analytics, if there's a need for that. At the very least, even if you don't need real-time analytics, what this technique does for you is it reduces how heavyweight the ETL processes are. So, in fact, virtually ETL as a bunch of code goes away, because the E part, the extract part, is now its ingestion through pub sub. The transformation part lives in that information layer that we talked about. So the E and the E goes away, the T is separated, and the load happens through that message queue out between the core and the information layer. I don't know if this is making sense verbally, but the idea is that I'm trying to eliminate that expensive ETL coding that is a problem in data warehousing.
And that you only do once for.
That's right.
Yeah. Okay. So you talked a lot about the data you want to analyze, and I was wondering, why is it becoming more relevant now? Why are we coming up with these things now? Does it have to do something with the buzzword big data?
Well, so I think in some sense it does. So I started my career in this field in early 1990s, 91 or so. My PhD and my master's degree both included artificial intelligence and machine learning. I got involved in data mining, which was very popular I should say data mining was a hot topic, kind of like big data is. Data mining was a hot topic in the mid-90s. The problem was that companies couldn't get a hold of their data to mine it. So they all liked the idea, but they didn't have their data well managed. So data warehousing became a big deal because companies realized that they would like to mine their data, but they couldn't do it. So now, flash forward 20 years. We now have these new technologies, these big data technologies like Hadoop and Cassandra and a variety of others. And many of the relational database vendors now have new technologies as well, in-memory databases, et cetera. All of these things have given rise to a whole new opportunity to analyze large volumes of data that we couldn't do 20 years ago. So I think that there's a couple of things. Big data has become an overused buzzword. It's unfortunate. It's also often assumed that big data also means data science. Those two don't have to. You can have big data management without doing any data science.
What does big data mean, actually?
Big data, I think that the term was actually coined in 2004. It was described in a Gartner analysis. Doug Laney is the... actually, I don't think Doug Laney coined the term, but Doug Laney of Gartner described big data using what are commonly known as the 3 V's: volume, velocity, and variety. Big data has large volume, so we now have the ability to store and analyze much larger volumes of data than we've been able to reasonably manipulate in the past. Big data has high velocity. It's coming at us very fast. It also decays very fast. So we might think of like a Twitter, the fire hose of Twitter data. It's relevant for a short time, but it's a lot of data if you want to analyze Twitter data. And then it's got a lot of variety. So now we have the ability to have, we can analyze video, we can do facial recognition, we can have audio, we can have text. So it doesn't all have to be relationally structured. It's got this wide variety of formats and structures, and we can bring all that together. So a lot of things, the use of audio data combined with metadata about the audio file, combined with an image, we can combine all of this and do really interesting data science. Not always good. It's like you. I know that the NSA has been in the news a lot for using analytics for very scary purposes. That's unfortunate because it's sort of with power comes responsibility, and it's questionable whether that's very responsible. But anyway, I got off track there.
Yeah. All right. So when this big data is like the thing coming up, does it create the momentum for what we call analytics these days?
It's made data science be a lot more possible and achievable for companies. There are 3 or 4 types of companies. There are companies for which data science is central to what they do. So companies like eBay, Facebook, Amazon, without analytics, they would not be nearly as successful as they are. I know the analytics director at eBay, and he made an interesting comment to me. He said, eBay doesn't make anything, they don't buy anything, and they don't sell anything. They just provide a platform for people to sell things to each other. So all they have is data to make their business and make the experience for their customers better. So data is central to what they do. So there's that first kind of company is the company that they know that data and analysis or data science is central to what they do. Second kind of company is a company that they recognize that there's value in the data, and they are looking for ways to create that value from the stored data. But they don't see data as being central to their business and their existence. So many traditional retail chains might fall into this category. These are, companies that have gotten by fine for years on intuition and experience. They know that they can benefit from data science or data analysis, but it's not, they can still get along without it. And the third type of company are companies that have data, but they don't realize that there's potential value in that hidden in that data. I often talk to clients and companies about whether their data is truly an asset or whether it's a liability. And my argument is that if you're in a company where all the data are being collected and stored, but nothing is there, it's not being used for anything, then it's taking up space, it's taking up people time to manage it. It's a liability, it's expensive. Whereas the companies that do a good job of analyzing and enhancing their data, they're turning that into a true asset. And so I encourage companies to consider how to make their data as much as valuable an asset as possible.
Let's change topic a bit.
Okay.
Why is it Agile Analytics?
So analytics by nature is not inherently agile. So
what would you define as agile?
So agile is the ability to create and deliver value early and frequently in a project. So whether it's a software project, let's start with software since that's where the agile movement came from. In the world of software, there are some companies or project teams that work in a what's called a waterfall fashion, which is design everything up front, do the requirements analysis, do the design up front, build and build and build, do tail end testing, and then deliver the solution all in one big bang at the end. Those projects commonly fail. They either fail to meet the true requirements, or they fail to deliver meet the expectations of the customers, the end users. So now what I've done with my book is to take agile software techniques and apply them to analytics. It's not a big leap, except that the world of data, the community of people that are working with data warehousing, business intelligence, data science, they're not the same people that are building software. So they haven't heard the software message, and even if they have, they haven't done a good job of understanding how these things in software can apply to
to
data.
their
Right.
yeah.
So the simply put, the agile techniques are typically fast iterative cycles of development where we do a little bit of requirements, a little bit of design, a little bit of build, a little bit of test, and we quickly showcase those working features to the stakeholders, and we elicit their feedback. We want to know how they like it, do they accept it, how do we adapt to that feedback, and in that process. And so this is every week to 2 weeks we're delivering new working features. In the case of analytics, we're delivering new either predictive models or new discoveries or new insights that business stakeholders can evaluate. They can say, this is useful, I can take action on this, I know what to do with this. Or they can say, can you go back and do a little bit more, do something a little bit different. So same concept, every week or two, we're trying to provide something of value. Meanwhile, we're continuing to iterate on the analysis. So, you might, a conventional data science project might run 3 to 6 months before it produces, good, accurate, predictive models. Agile data science or agile analytics, we would produce an early predictive model. It might not be really as accurate as it could be, meaning maybe it's better than flipping a coin, but not by much. So think my credit fraud example. It might be an early predictive model that kind of predicts credit fraud, but it misses a lot of the time. And then we iterate on that and iterate on that. So we're incrementally making the accuracy better, but we're also getting feedback from the business to make sure we're doing the right thing and using the right approaches.
So how do you achieve this? So because you said not all analytics projects work this way. Why is that so? It sounds so obvious when you tell it.
It does, doesn't it? So the first problem is that the Agile movement in software blew up around 2001. Actually, 2001 was when the Agile Alliance was formed and the Agile Manifesto was signed. That was the core group of 17 people. Martin Fowler, who was another thought worker, was
and another show guest from some episodes ago.
Yes. Okay. So another. So the movement started it started a little bit before this, but 2001 it kind of consolidated. By about 2004, the software community was really starting to pay attention, meaning that companies like banks and insurance companies were starting to say, hey, this looks like a better way to develop software. The problem is that the data community didn't start paying attention until about 2009 or 10. I started writing about this in 2004, about using Agile for data warehousing in 2004. My book came out in 2010, actually 2011. And I was first asked to speak at a conference on this subject in 2010. And I think I was the first, this was a Data Warehousing Institute World Conference. And I was the first keynote speaker to have spoken about Agile data warehousing at that time. And it was a very new concept to people in the data community. So the data community has lagged behind software in picking up this Agile approach. I think it's confusing for a lot of people. Software is about custom building functionality from raw code or source code. Data management, business intelligence, advanced analytics, it's a different, it looks and feels different. So it takes some abstraction and generalization to think about how to apply these techniques. So the guiding principles are deliver value, collaborate frequently with your stakeholders, and working software or working analytics in our case is the measure of success. We can stick with those values, and we can adapt the practices to work for data science. But it's new to a lot of people. I think that's the biggest problem.
And what kind of practices do you employ?
So what I've tried to do, now this actually looks different in data science than it does in data warehousing. So for ETL development in a data warehouse environment and for data modeling in a data warehouse environment, what I've tried to do is take a lot of the software practices and adapt them to ETL development. So things like test-driven development, pair programming, use of patterns, refactoring, those ideas all apply to ETL coding, but they're tricky to apply because we're not writing, like the data warehouse practitioners aren't using languages like Java or Ruby or other languages to write this ETL code. They're using a commercial software package. So figuring out how to test it, how to do unit level testing, that's kind of a new concept. But those practices are conceptually they apply. So the things that the software community, software developers are doing apply to ETL. Data science is a little different. So in data science, what we do is we may try out a dozen different models or algorithms before we hit on one that's going to start to produce some good results. So we may write a lot of throwaway code in the process of figuring out which algorithmic technique or which models are going to become relevant. So I often describe this as a lab phase and a factory phase. So the lab phase is where we're hacking code, we're moving quickly, we expect to throw most of that code away. And as soon as an algorithm or an approach starts to look like it's going to be keepable, then we need to transition into a factory mindset where we need to put tests around the code. In the case of Python, there's unit test framework for Python. There's behavior-driven development for Python. So as you transition from this lab mindset to a factory mindset, a data scientist, especially pairing with a good developer, can start to put tests around that code. I don't know about patterns usage quite as much, but I'll go back to my credit fraud detection example. What ultimately has to happen for that to be a good model is the model goes into production against live streaming data. So as soon as you swipe your credit card or the vendor swipes your credit card, that transaction goes over the wire. It runs through this analytical model, which scores it and says, this looks like a fraudulent transaction, and it gives the vendor back a message that says card declined. Yep. And that happens like really fast. So that means that the predictive model got built in the lab, validated and verified in the lab, and then the developers working with the data scientists had to actually write production code or turn that code into production quality code and put it into action. In that case, the agility starts as you transition from the lab into the factory, and then it's like software development.
Yeah. It's similar to a software development project. Oh, okay.
Exactly.
All right. So as our time is nearly up, is there a question you would have liked me to ask, or is there anything you want to say as closing words?
Oh, let's see. Yes. So the question that I think we should all be asking is, what is the future of data science? So the interesting thing that we've been talking about requires a lot of human work, expertise, skills, and time. Now we are moving into a world where everything produces data. Your car is loaded with data. Your mobile device is loaded with data. If you have a Fitbit or a biomedic or what are they called? Personal health, a wearable device. Those things create data. Everything is creating data. So So the question is, what does that look like? How can, if it takes months, weeks to months in order to produce good data science results, how can we possibly deal with this explosion of data in a meaningful way? Isn't it all just going to pile up and bottleneck? And so my prediction is, my theory is that we're going to move into a place where we write algorithms that and this has been done a little bit, but we'll start using more and more algorithms that will just continuously try to build predictive models automatically, and many of these models will be junk, they'll be thrown away, but the ones that start to hit and start, the machine can be doing the automated data science in the background, and as soon as it starts creating a prediction that's worthy of attention, it can bubble that up to maybe a human expert to evaluate. So if we think about big data as being massively parallel computing to manage data or to process data, now imagine a massively parallel data science, automated data science process, so that we're not just processing the data, we're actually doing predictive model development, like in real time, round the clock. Some models live, some models don't live. I think it's kind of fascinating. I don't know exactly what that looks like, but I guess I'll add one more thing, and you can edit this however you see fit. The other question you didn't ask and we didn't get into is the ethics and morality of all of this. So usually this discussion of data science also triggers questions about the ethical use of personal data, medical data. I know in Germany you have very strict laws and regulations around how data can be used. The rest of the world doesn't have that, including America. And it's a big problem. If a company is using its customers' data irresponsibly, customers will cry foul very quickly, and the company will lose customers. The government agencies, they somewhat are the same way, except they're less responsive to the people saying, you can't do this. So in my country, we unfortunately have used 9/11, the events of 9/11, as an excuse to give our government permission to use our data in less controlled ways, and it's scary to me. And I think that one of the things that we need to establish globally are some rigorous standards and rules and guidelines for how data can be used and cannot be used. So
especially as it's all statistics and therefore it can be wrong.
That's true.
What the software predicts about you.
That's exactly right. It can be wrong. It can be used to profile people in ways that are not. It could be detrimental. So that's There's a potential to misuse data science, and as much as I love this field, we have to be very responsible. So that's the other question that you didn't ask.
All right. How can people find out more about all this Agile Analytics you're doing?
So Agile, if you do a Google search on Agile Analytics, you should find my website. There are starting to become more books available in this subject. One book that I've recently gone through is a book called Agile Data Science. It's quite good. It's actually a good example of using Hadoop to do Agile data science. There is the community that are doing Agile in data warehousing, business intelligence, and data science it's growing slowly, and it seems there seems to be more and more resources coming available for
We will link to these in the show notes as well, so
Okay.
you don't have to type them. All right. And how can people find out more about you? So you mentioned your blog. Are you on Twitter or anything else?
I
How
am
can
on
people
Twitter.
get in contact with you?
Sure. My Twitter handle is TheAgilist, TheAgilist. My email address is kencollier@theagilist.com, KenCollier. And I have a website that's theagilist.com. So, and I try my best to put usable, consumable information there. It's been a little while since I've posted a blog there. I need to do that, but you can contact me through that.
Okay,
page
perfect.
As well.
Any upcoming speeches?
Let's see. I'm going to be, as a matter of fact, I'm going to be in Copenhagen in early September. I'll be speaking at the information, it's called IM 2014 conference. And I think if you go to im2014.net, I think that's the website for that conference. I'll also be teaching in London through the Data Warehousing Institute. I'll be teaching a seminar series, 3 days of Agile Data Warehousing and BI topics, and that'll be also in early September. So you can find that on the TDWI website.
Okay, perfect. Then thanks very much.
You're welcome.
For being on the show. It was very interesting.
My pleasure.
I mentioned again the show notes, so all the stuff you mentioned will be available, so people don't have to Google and find out these things extensively. We would actually like to have feedback how you liked the episode as our listeners. So either go to iTunes or use our blog to comment on it and maybe tell us what you like the most and what you like the least about this episode. That's all for now. Goodbye from SE Radio. This is Johannes speaking. Bye.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To support us, you can advertise SE Radio by clicking the Dig, Reddit, Delicious, or /Thought buttons on the site, or by talking about us on Facebook, Twitter, or your own blog. If you have feedback specific to an episode, please use the commenting feature on the site so that other listeners can respond to your comments as well. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks again for your support.